What's up, guys? We are still deriving our equations for batch reactor, especially in gas reactions when we have change in moles. And I know probably this is kind of boring because we are just doing equations, but it's very important that you know where does these equations come from, because in next chapter, chapter number 4, we're going to apply all those equations, and it's very important to know when can we apply equations and when can we apply them. So, okay, let's do the batch reactor stoichiometry table for changing moles, especially in gas reaction. And probably you know that if you have a gas, you can model it by ideal gas or by the C compressibility chart uh, model here, which is on the DC, or finding the C and correcting the factor. Our study is based on real gases, so if it's ideal, just assume that C0, or the initial C, is the same as the final C and it's 1. And what does that mean? By definition is ideal gas. So you got PV equals CnRT, and if C is 1, you will get the ideal gas equation. Now initial conditions, pressure times volume equals the C value at the initial times the total amount of moles times the R, which is a constant, and the temperature at the initial condition. Final conditions, I will write this here. So let's suppose we want to divide the final conditions here, or this final equation, and the initial conditions, which is here. We will get this value here, which is of course a little bit confusing, but just know that we can arrange our values here. And of course this is 1, because a constant divided by the same constant equals 1. And we get this equation here. We're going to use that equation. The total amount of moles that you see is the initial amount of moles plus the change in moles depending on the conversion of A. So where do we got that? We got it from last tables, so please go up if you have no idea where do we got them. An important note on this value. This value by definition is the change in moles. So if you have 0, you have no change in moles. If you don't have 0, you have a change in moles. So if it's positive, you increase the amount of moles at the end, and if it's negative, you decrease the amount of moles at the end. Okay, you can treat this as a liquid phase reaction. So if you've got this value here, please ignore everything we're going to do, because you can model it as we've modeled it before. And actually you can go back to the video, the batch reactor stoichiometry table for liquid phase reaction. Now, what happens if we do have a change here? So you can see NT 0 when you have 0 here. But this is not the case. We're going to have a change in moles. So how do we account for that? Okay. Let's divide everything by these NT initials. So NT initial is here. We divide all this by NT initial. You can see here is going to be turned out to 1, and this is going to be turned out to mole fraction. So this is 1. No, sorry, this one is 1 equals, no, plus the change here. We just rearrange this value here, or this value here. It's mole fraction, of course. By definition, mole of A at the beginning is the moles of A at the beginning divided by the total amount of moles, which is this value. So we got this, we let this delta here and XA. Now the book calls this epsilon, this multiplication of the initial amount, or the initial mole fraction, times the change in moles. So we can say that at any time the relationship of this is 1 plus epsilon and the conversion. So just learn it as an equation we're going to use later on. Now let's go back. Probably you remember this. Pressures times volumes times C times moles times temperature. Let us find out volume, because we are analyzing the change of volume. So this goes dividing, this goes multiplying. Okay, we got this. Volume out, pressure, temperature, C factors for real gases, and we are substituting this value here Where do we got that? Remember, we got it from here. So this is this. So we got nt divided by nt0. This is exactly this value here. Hopefully you don't get mixed. And just one note, if we were going to model this gas as ideal, we can cancel this because this will be 1. And if we have no change in pressure, we can take away that. And besides that, we are working with isothermal design. We can take away the temperatures and the volume will change because of this conversion and epsilon. If we have 0 conversion, we have that volume 1 equals volume at the end. If we have 0 change, remember epsilon is just epsilon times mole fraction times this delta, sorry. If we don't have a change in volume, this will be 0. So 0 times this will be 0, and epsilon will be 0, and epsilon times x will be 0. So our final volume will be also the same. So when do we have this change? When we have conversion and when we have a change in volume, guys. So perfectly, hopefully you get the idea of how we are going to model this here. Just be sure that this correction of volume is when you have mole change. So if you of course have no mole change and you want to use that equation, please be sure that you get to this conclusion. Note that for batch reactor, the volume usually doesn't change. Why? Because they are fixed vessels. So you got this tank here, you are mixing, and it's very strange that a batch reactor changes in volume, but you do have some cases in which maybe you got this piston here and it changes as pressure increases and you have a change in moles and change in volume, so you have the case in which you do change it. So I think that's everything for batch. We're going to continue with the continuous flow reactor. This is more common that they have a change in volume. So let me open a new video. We're going to see this topic in that video. What's up guys, it's me, Chemical Engineering Guy. So if you like the video, why not push the like button? It really helps me to know if you're liking the videos or if I should be changing something or I should be adding something, taking out content, whatever. Also, sharing is caring. So if you got any kind of friends, teachers, colleagues, or whatever kind of person that might be interested in this type of content, why not share it? Sharing helps our community to grow faster in members and in content. If you want to keep track of my activity, videos, uploads, experiments, playlists, whatever content I'm getting on YouTube, be sure to click the subscribe button. Subscribing to the channel is totally free, guys. My dream is to create an online academy of chemical engineering, where everyone can access it in the world. Imagine a place in which the student, the teacher, and the engineer get the best of each other. So thank you guys for the support and the love.